Alright, hi everyone, welcome to the second discussion video. So this is section 3's worksheet where we're going to be covering the first problem on CSPs and the second two problems on games. So the first problem is formulating traffic control as a CSP. So we have 5 planes and 2 runways. The runways are not important until part B, so I'll be going through part A first, so we're going to ignore temporarily that there's 2 of them. We're noticing that they have 4 time slots for each runway to schedule landing and taking off of a plane, and we're trying to find an assignment that meets this bullet point list of constraints. Okay, so the first problem is asking us to find the variables, domains, and constraints. So the variables are simply the planes in this scenario, so A, B, C, D, and E. And the values in this domain are the time slots. So 1, 2, 3, and 4. So with this formulation, we're just trying to assign a time slot that works to each of the planes because we're trying to manage their landing and takeoff in this airport. Okay. Now we're going to go look at the constraints. So the first bullet point for the first constraint says that plane B has lost an engine and must land in time slot 1. So this can be expressed mathematically as B, the value has to be equal to 1. The second bullet point says that plane D can only arrive at the airport to land during or after time slot 3. So this is equally formulated as the value of D is greater than or equal to 3. All right. The third one says that plane A is running low on fuel but can last until at most time slot 2. So this is also another inequality. The value of A has to be less than or equal to 2. Right. Then plane D must land before plane C takes off because some passengers must travel from D to C. So this is our only binary constraint, and we can formulate this as the value of D has to be less than the value of C. Okay. And then the last one says that no 2 aircrafts can reserve the same time slot for the same runway. So notice, as I said before, that we're going to be temporarily ignoring that there's 2 runways. So we're just going to specify it as A cannot be equal to B, cannot be equal to C, cannot be equal to D, cannot be equal to E. So we're assuming here that they all have to be landing on the same runway. So you'll notice that in this current formulation, there's actually no solution because there's 4 time slots, 5 planes, and none of them can have the same time slot. All right, so we've solved part A, so let's move on to part B. Oops. Okay, so in part B, part I, part B, here's where the runways actually become important. So you'll notice that A, B, and C cater to international flights, so they use the international runway, and then D and E cater to domestic flights, so they only use the domestic runway. So we're no longer assuming that they're all using the same runway as in the previous part. So we will have the same constraints of B is equal to 1, D is greater than or equal to 3, A is less than or equal to 2, D is less than C. But in this scenario, instead of having A not equal to B, not equal to C, not equal to D, not equal to E, we're only going to have A not equal to B, not equal to C, and D not equal to E. Right. And so in this case, having these constraints, our constraint graph becomes, so let me draw in the variables, A, B, C, D, and E. So in this case, A, B, and C are all interconnected because we have that their values cannot be the same. We have D and E are interconnected because their values cannot be the same. And then D and C will be connected because of the constraint that D has to be less than C. Okay, so now we are moving to part 2. So we're going to be enforcing arc consistency on these domains. So I'm going to start off by enforcing the unary constraints. So before you run arc consistency, you always enforce the unary constraints before stepping through the normal procedure of taking arcs off the queue and enforcing the arcs. So B has to be equal to 1, so we remove the values 2, 3, and 4 from B. D has to be greater than or equal to 3, so we remove 1 and 2 from D. And A has to be less than or equal to 2, so we remove 3 and 4 from A. So what I think is most intuitive in this case is drawing out all the arcs in the queue. So given that we have 5 edges in the previous constraint graph, we're going to have 10 arcs because each constraint is represented by 2 arcs for both directions, right, as 2 directed edges. So I'm going to organize the arcs by the order that I find is going to be easiest to enforce in. So this will take a while to write out. B is pointing to A, C is pointing to A is pointing to C, B pointing to C, D pointing to C, C pointing to D, E to D, and D to E. So I may have picked an arbitrary seeming order, so note that order of the arcs in the queue will not affect the end solution that you get from arc consistency. It may end up changing how long it takes, so the runtime. So depending on the order of the arcs, if you pick a bad order, then you might add back arcs a lot of times, and then it will run for a long time. But the solution will always be the same regardless. Okay, so you may notice that I've organized it by what it's pointing to. So in this scenario, if we follow the arcs, we're going to be enforcing all the values that depend on B, then A, then C, then D, then E. So we're going to go through this. So first we look at A pointing to B. So we pop this one off. So scribble that out. So A pointing to B, we notice that based on the constraint that A cannot be equal to B, we have to remove the value 1 from A. So we enforce that. Right? So normally in this case, we need to add back all the arcs that then point to A, but they are already on the queue, so we do not need to add them back. All right. Then we enforce C pointing to B. So similarly to A, we need to remove the value 1 from C because C cannot share the same value as B. So note that when you're enforcing an arc, you remove from the tail, so tail points to head. You remove from the tail, you check for every value in tail that there is a value that satisfies the constraint in the head. So the reason we remove 1 from C is that we look at the value 1 in the domain of C, and we see that B having the only option of being 1, and so C assigned to 1 and B assigned to 1 violates the constraint. So we need to remove the value 1 from the domain of C. All right. Similarly, even though we changed the value of C, or the values in the domain of C, we do not need to add it back to the queue because the arcs pointing to C are already in the queue. Okay. Now we go to B pointing to A, so 1 and 2. This is fine, they are not equal. So we've done checking that. C pointing to A. So in this case, we also need to remove the value of 2 from C. This is because A only has the value 2 left, and again, the value of C cannot be equal to the value of A. And so, of course, normally we would go add back all the arcs pointing to C onto the queue, but again, they're already on the queue. All right. So then we have A pointing to C. This is fine. 2 and 3 and 4, 2, 3 and 2, 4 are both valid assignments. Okay. We have B pointing to C. Again, this is fine. 1 and 3 and 1 and 4 are both valid assignments for both of the variables. Okay. Now we have D pointing to C. So the constraint between D and C is a binary constraint where the value of D has to be less than the value of C. So in this case, we prune the value of 4 from D. This is because 3 is fine because if you assign 3 to D, you can assign 4 to C. But if you assign 4 to D, there is no value in C that D will be less than. All right? So we alter the value of D. All right? That's done. So then we go back and look at C to D. So looking at C to D, we need to remove the value of 3. This is again by reverse logic. C needs to be greater than the value in D, and if C is assigned to 3, there is no value in D smaller than 3. All right, now in this case, after we've changed the values in the domain of C, we do need to add back all the arcs pointing to C into the queue. So this means we add back A to C, B to C, and D to C. Okay, so we can go through these really quickly. You'll see that once we enforce these, nothing changes because 2 assigned with 4 and C is fine, 1 assigned with the 4 and C is fine, and 3 assigned with the 4 and C is also fine. So none of these arcs, once they're enforced, none of the values in the domain change. All right, now we need to go look at E to D. So in E to D, we remove 3 from the domain of E, again because D cannot have the same value as E. So we remove this. We need to add back all the arcs that are pointing to E, but this is the last arc in the queue, D to E. So D to E3 is fine with all of the values of E. We pop that off the queue. The queue is now empty, and this is the answer after we finish enforcing arc consistency. Okay, so great, we finished arc consistency. We found a solution of sorts. So the next problem is discussing another way to try and find a solution. So basically the premise is that arc consistency is sometimes expensive to enforce, so we're trying something else. We're doing forward checking on variable assignments. So the way we're going to pick the variable assignments in this case is using the minimum remaining values heuristic by doing backtracking search, and breaking ties by picking lower values and characters. Okay, so minimum remaining values heuristic is the one where we pick the variable with the fewest remaining values in the domain. So fewest values in the domain. Okay. Right. It'll be, if it's a little confusing just by the explanation, it's going to become clear after we do the problem. So like we do in arc consistency, we start off by enforcing all the unary constraints. So this is essentially removing the 3 and 4 for A because A has to be less than or equal to 2. Removing 2, 3, and 4 from B because we know B has to be 1. And removing the 1 and 2 from D because we know that D has to be greater than or equal to 3. Okay. So starting off this way, we can see already that B has the fewest values in it because it only has 1. So the first variable assignment pair is B1. So after we assign this, we need to run forward checking. And forward checking is essentially, once we assign a variable, in this case B, we check all the arcs that point to B. So in this case, it's A to B and C to B, right? Still going by the arc notation. So we remove 1 from A because A cannot be equal to B, and we remove 1 from C because C cannot be equal to B as well. Okay. After this, moving on, we see that A has the next fewest remaining values. It also has 1 now, so B is assigned to 1. This is fixed. So then we assign A 2. Okay. So A is assigned to 2. So again, we're going to enforce all the arcs pointing to A. I'm not going to write out the arcs. It basically affects C because C cannot have the same value as A. So we remove the value of 2 from C. Okay. So in this case, we see C and D have the same number of values in them now. But remember, we're breaking ties by lower values and characters. So this means we go assign to C and 3. Okay. At this point, the constraint that comes into play is that we have to have the value of D is less than the value of C. So if C gets assigned to 3, then when we're enforcing the arc D to C, we quickly realize that there are no valued values left in the domain of D. So this is where we need to do backtracking because we see there's no solution for this assignment to C. So in this case, we revert the assignment of 3 to C, and we do not assign it in the next step. So our order still contains C to 3 because this is part of the backtracking search. We still assign 3 to C, but after we see that there's no valid solution for assigning 3 to C, we revert the assignment and we move on. So by moving on, I mean we assign C to 4, which is the next value in the domain. So this does have a solution. Oops. This does have a solution because D less than C still means that we can have a 3 in D. So we remove that. So technically, we are enforcing the arcs between A and C and B and C in this step of forward checking of assigning to C, but nothing is changed after enforcing those arcs. Okay, so we've successfully assigned C at this point. The next value to assign is 3 to D because D only has 1 value left. So D, 3. Run forward checking, we remove the 3 from the value of E. And then after this, we assign E to 1 because E is the only value or only variable with values left in its domain. We're picking the smallest number going by the tie-breaking scheme, so E is assigned to 1. All right, so moving on to the last problem on question 1 about CSPs. So suppose we have just one runway and planes where no two planes can use the runway at once. So we're going back to only having one runway. So we know that the constraint graph is tree structured and that we know that a solution exists. So what's the runtime complexity in terms of the number of planes and that of a CSP solver that runs arc consistency and assigns the variable in topological ordering? Okay, so we are given that the runtime complexity of solving a tree structure CSP is ND squared, where N is the number of variables, so variables, and D is the size of the domain. So I'm not going to go over in this discussion video specifically why the runtime is this. I think it's more important to understand exactly how a tree CSP is solved. But if you guys want to know more, I highly suggest looking at the lecture notes because I think that has a pretty good explanation. But anyway, so in this problem, we know that we have n planes, which is the number of variables. The main blockage to finding the runtime is that we don't know the domain size. So here we see that a solution exists and that we have one runway. So we basically assume that because we know a solution exists, we know there are at least n values in the domain. If there were any less, we would not have a solution, right? And in this, the runtime converts to O of n cubed for solving this tree-structured CSP. Cool. So we finished working on the CSP problem. We're going to be moving on to games. So I think there's not too much conceptual material that works with games in terms of alpha-beta pruning and running minimax and all that kind of thing. It requires more practice than anything. So this problem is asking us to perform minimax and to perform alpha-beta pruning. So these pointing down triangles will represent the min nodes, and this pointing up triangle represents the max nodes. This is always the case. It's just convention to draw it this way. So we're just going to mechanically run through minimax. So the first min node takes on a value of 3. The second min node takes on a value of 2. The third one takes a value of 4. And then the max node looks at 3, 2, and 4, takes the max 4. All right. I think that was pretty self-explanatory. So the second part is asking about alpha-beta pruning, which is a kind of trickier concept. So the goal in alpha-beta pruning is that we know that if the max node will never pick the node that we are currently calculating the min for example, then we can stop looking at the rest of the children, which is an optimization when we are running minimax or a game tree algorithm. So when we're running minimax, when we do 10, 8, and 3, we get the first value to be 3 in the first min node. Then we look at 2 in the second minimizing node. And at this point, this is where we can perform the alpha-beta pruning in this tree. This is because we know that the value in this node is at most 2, because this is a minimizing agent, and so that the value in this node can only be smaller than 2, not greater than 2. And because we know the maximum of this node is 2, we know that the first minimizing node has a value of 3. We know that the maximizing node above this is always going to pick the first one. And so because we know the maximizing node is going to pick the first node instead of this second minimizing node, because the value is at most 2 here and the value is 3 here, and 3 is always bigger than 2 or any value less than 2, we can stop looking at the next values under this minimizing node. So in this case, 15 and 7 are pruned. All right. Then we move on to the third minimizing node. We see that it has a value of 6 in the first leaf. 6 is greater than 3. So we know the maximizing node can still pick this one. So we go on. Then we go look at 5. 5 is greater than 3. And then we look at 4. 4 is still greater than 3. So we ended up pruning nothing in this last one. 4 is assigned to the minimizing node. And then the max picks this 4. All right. In essence, alpha-beta pruning focuses on, in a minimizing layer, finding the biggest value seen thus far. And then in maximizing layer, you focus on the smallest. So this tree is too small to perform any pruning on the maximizing nodes, but the key idea here is that by keeping track of the biggest value, that we have seen thus far in these minimizing nodes, we can avoid checking some of the leaf nodes when we know that we're no longer going to be picking the minimized node in the next maximizing layer. So we no longer look at 15 or 7. So just to be absolutely clear, 15 and 7 are the nodes that are pruned. And that means we do not look at them when running minimax. So we do not look at them because we know that regardless of these values, the maximizing node will take 3 over 2, or any value less than 2. All right, so this is the first part of number 2 completed. The second part is introducing a new tree. So these circles are chance nodes. So this just means we're taking the average over the children instead of doing the minimum or maximum as we've seen below. Okay, so the math is 10 plus 8 plus 3 is 21. So divided by 3, the value here is 7. In the second one, we do 2, 15, and 7. This value is going to be 8. They add up to 24. And in this one, we have 6 plus 5 plus 4 is 15. Divided by 3 is 5. And the maximizing node will take the value 8. Okay. So 4 is asking again about alpha-beta pruning. Can we prune anything from this tree? The answer in this case is no. Because in alpha-beta pruning, we knew that there are specific bounds that the maximizing node was going to pick. Okay, so the idea is that when we got 7 in if this was a minimizing node and we got 7, then we know that the value is at most 7. It's upper bounded there. But the problem with the expected max nodes, or the chance nodes, is that if we see 10 and 8 in the first 2 leaf nodes, then the last leaf node can be any value that skews it above 7 or below 7. So the same applies for like any of these. So depending on how many leaf nodes we see, we cannot simply ignore the leaf nodes we have not yet seen because it can skew the value in any direction. Unlike in maximizing, where we're going to have a lower bound, or in minimizing, where we're going to have an upper bound based on the leaf nodes we've seen thus far. So no, alpha-beta pruning does not work when we have chance nodes in this case. Okay, non-zero-sum games. So previously we were working with zero-sum games. This means that if player A gains something, then player B correspondingly loses that same amount. So this is why we're using the minimax tree, because Pac-Man, a positive score is what Pac-Man is trying to maximize. And for the ghosts, they want lower scores. So they're operating on the same value. A just wants a higher value, B wants a lower value, and A's gain is directly B's loss. So in non-zero-sum games, there's no such correlation necessarily between the scores. So this is represented as having 2 different utilities for 2 different players. So let's see. The first value here is player A's utility. The second value is player B's utility. Okay. So they're trying to maximize their corresponding utility. They're no longer operating on the same value. So B tries to maximize its own. So this means it puts 3, 5 in the first node, 15, 9 in the second node, and let's see, 4, 12 in the third node. And then at the top, A is going to pick 15 and 9 because 15 is the biggest value for A's utility. Okay. So what nodes can be pruned above through alpha-beta pruning? So as before with the chance nodes, we cannot alpha-beta prune anything from this tree. This is for a different reason. It's because there's no more relation between these scores, right? So there can be a node that is good for both B and A in this scenario, and one person's gain does not directly correspond to another person's loss. So simply put, there's just no relationship between the utilities. We can't really say anything about A's utility when we have B's utility, and you can't perform alpha-beta pruning on this.